Okay, here we go. Last problem here of this uh, test on line or this old test on line integrals. So um, we want to calculate the flux. I was really clear about that because I want to make sure everyone knew. Um, uh, Around this semicircle with this vector field, xy squared, 3x squared y. Um, and this has a radius of 2. So my flux is, there should be a little hat over this n. The integral over c of f dot with n hat ds. Um, so this is one that we're using Green's theorem for as well, the normal version of Green's theorem. The second one that we did, I think this was like sort of when, this is one of the last days we had like in-person class. So it might, you might, I don't know how much we practiced, but um, anyway, we got M, we got N, same thing. This is like exactly the same as the other um, uh, Green's theorem problems, except for we don't do the curl. Instead, we do n sub y plus m sub x, or m sub x plus n sub y, however you want to think of it. So I do the double integral over R. This line integral turns into the double integral over R, where R is that region, dA. I've got a y squared plus 3x squared dA. Um, in this case, I look at it and it screams polar to me because of the region that I have right there. So I quickly convert it to polar. 0 to pi this time, not 2 pi like the last one. And then 0 to 2, because of the radius of 2, of, I'm not going to go over it the way I did in the last one, but y squared is r squared sine squared theta. Um, the 3x squared turns to 3r squared cosine squared theta. And then I've got my r dr d theta. The r dr d theta is the dA. You should be pretty good with that. So from there, um, there are there there are lots of ways to do this one, and like when I gave this as a test question way back when, um, I don't I don't think the majority of people did it the way that I did it here, at least in terms of this conversion. I think a lot of people did um, power reduction, double angles on that, and double angles on that. I sort of looked at it, I factored my r cubed out. It was this r squared, that r squared, those guys times an r, so that's r cubed. And then I have sine squared plus a 3 cosine squared. Instead of doing the double angle, which you could do it and it would work on both of these, I said, well, look at this. I've got sine squared plus 3 cosine squared. Let me think about that as sine squared plus cosine squared plus 2 more cosine squared. Well, the sine squared plus the cosine squared gives me 1 by the Pythagorean identity, and then I am left with 2 cosine squareds after that. You don't have to do this, but I think it makes it easier if you see that part. So my inner integral is integral 0 to 2 of r cubed this, 1/4 r to the 4th. This does not change. When I evaluate it at 2, I get 4 times this thing. Then I do my outer integral. I move the 4 out front. I've got a 1 plus 2. This is where I use the angle reduction, or the, excuse me, power reduction double angle formula. Cosine squared theta turns to cosine squared 2 theta plus 1 all over 2. This 2 is that 2, so they cancel out. I've got 1 plus that 1. That gives me this 2. This has a coefficient of 1 because these guys canceled. I'm going to integrate that from 0 to 2 pi, or sorry, from 0 to pi. That gives me 2 theta plus sine 2 theta over 2. Evaluated, the 0 got cut off there from 0 to pi. And once again, the signs cancel out because sine of, if I pop the theta or the pi in there for theta, I get 2 pi, which goes to 0, and then the sign at 0 is also 0. So this term goes away. I get 4 times 2, times my theta, evaluated from 0 to pi, which gives me 8 pi. So if you did it maybe by doing a power reduction on that guy and that guy individually, you should wind up getting the same answer. I think it's just a little bit more work. Anyway, hopefully you're good with this, and send me like a comment on Google Classroom, email, whatever, if you need some additional help. Thank you. Bye.